My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's session on Atomic Force Microscopy, and we're extremely lucky to have AFM Workshop represented by Dr. Paul West to explain that to us. Just briefly, if you're not familiar with who the Graphene Council is, we're a global trade and professional body for the sector, and part of our mission is to educate and inform people about what graphene is, how it's produced, how to obtain it, how to apply it, how to use it. And that includes the writing of technical standards on how to characterize and measure graphene. And that's where atomic force microscopy comes in as one of the important tools that we use to do that. So that's what today's session is going to be focused on. And we'll get started now. So Paul, if you want to go ahead and pull up your presentation slides and share your screen. Then we'll hand it over to you, and you're going to teach us about AFM.
Okay, thank you. I'd like to start out today by thanking Terrence and the Graphene Council for hosting this webinar. I think it's a great opportunity for everybody. And I also like to thank everybody who's attending for taking the time to hear this presentation. AFM Workshop is a company that's located in Hilton Head Island, South Carolina. We specialize in making atomic force microscopes that are considered to be very high performance for a reasonable price. And this presentation is some of the work we've done in imaging 2D materials. It's not an exhaustive presentation, but it'll give you some of the insights into what's important when you consider using an AFM for imaging graphene and other 2D materials. So the first question people say is, why do I need an AFM? There's a lot of other microscopes out there, optical microscopes, TEMs, SEMs. And so what sets AFM apart from those other instruments that are these following items? The first thing is we can measure the height of 2D materials down to the atomic scale. And it's not very difficult once you learn how to do it. These microscopes are relatively low cost to purchase. Under sort of $50,000. There's a low cost of ownership. Once you own one of these microscopes, there's not a lot of maintenance associated with them. Once they're up and running, they'll usually run for 5 or 10 years with a lot of maintenance, other than sort of calibration. And for the most part, you have very simple sample preparation. There is some preparation involved, but it's not very complicated. You don't need a lot of complicated equipment. So today's agenda is this. We're going to do some AFM theory. We find that if people take the time to learn how the microscope works, they're more successful with it. We're going to go through some example images that mostly come from our customers. We're going to talk about sample preparation. And then one of the important issues is, how is the AFM calibrated to make sure that when you do Z-height measurements, you're getting the right numbers. And then I want to give a slight presentation on the difference between metrology and making pictures, because there's a slight variation there in how you process the data. And then we have a short 5-minute demonstration at the end. It's a demo that we recorded just to show you how the AFM works. Okay, so an atomic force microscope uses a stylus or a needle, and it scans it over the surface. This animation here kind of shows how it works. And as the needle scans over the surface, we record a line. And then we move the needle down a step and measure another line, and another line, and another line, until we can build up a 3-dimensional rendering of the surface's image of the surface. And so the secret of the atomic force microscope is that it's built so that it has very low loading forces on the needle or on the stylus. It's on the order of nanonewtons. And because it's a very low loading force, you can use a very small tip on the size of nanometers. That allows us to get very high resolution images. This schematic here or animation shows how the microscope works. It's quite simple in design. So you have a laser which shines off the backside of a cantilever into a 2-section photodetector. The output of that photodetector is then fed through a feedback circuit into a piezoelectric ceramic. So if the cantilever starts to bend up, the Z piezo down here goes down. So that feedback loop guarantees that this cantilever stays bent the same amount. And once you start to scan, the amount of voltage that's required to make that ceramic move up and down is recorded by a computer and displayed on the screen. And so that's how you generate an image. So in principle and in practice, learning how to run these microscopes is about as much effort as it takes to learn how to drive a car. And we'll talk about that later. So there are two basic scanning modes for measuring topography. One is called non-vibrating or contact mode. The other is called vibrating mode or tapping mode. And in the non-vibrating mode, you just measure the deflection of the cantilever and you keep that constant as you scan across the surface. So the ZPA that goes up and down to keep that constant. In vibrating or tapping mode, you vibrate the cantilever and you use a feedback circuit to keep the amplitude of vibration constant as you scan across the surface. The advantage of vibrating mode over non-vibrating mode is that you can have much lower forces on the order of piconewtons of force between the tip and the surface. So most scanning on graphene and 2D materials is done in tapping mode or vibrating mode. One of the key aspects of the atomic force microscopes is having a very sharp probe. And this is a picture of a probe. It's made with MEMS technology, and it's an anisotropic etch of silicon to create this point. And this point is as small as, on an average tip is 10 nanometers in diameter. On a really good expensive tip could be maybe 2 nanometers. Now, these probes cost between 10 and 30, between 20 and $50, depending on how sharp it is. Most of the people that do graphene work or 2D materials use a $20 tip. And we get the question, how long does the tip last? Once you learn how to use the microscope, tip can last a week or a couple weeks. But when you're learning how to use it, sometimes you break the tips and you have to replace them a little more frequently. Okay, so one of the key concepts that you have to understand for using an AFM for measuring 2D materials is what's called the noise floor. And in the noise floor, what you do is you hold the probe above the surface, you just hold it fixed, you don't scan, and you measure the chatter between the tip and the surface. And you get what's called a noise floor image. And so that's a measure of the smallest thing you can see. And so this right here is a noise floor image measured on one of our microscopes. And the noise is 20.4 picometers. Okay, so a graphene layer, a single graphene layer is about 800 picometers. So with this level of noise, you're going to get a very good signal to noise, and you're going to get a very clear image. And I'll show you what that looks like in a little bit. Okay, so one of the things about these microscopes is that you have to make sure that you're in a reasonably quiet environment. Sometimes people try to put them in rooms with a lot of fans and pumps and things like that, and that will reduce the noise floor of the instrument and degrade the performance. So just to go through something here, what does it take to be successful with an AFM? Just follow these 4 simple things. Number 1, find a good site. AFMs love basements. They love small rooms with no fans. Learn how to do sample preparation, take some time and read about it a little bit. Learn how to control the instrument, what the basic controls are, how to get the tip on the surface and how to do scan and what scan rates to use. And then finally, you have to do image processing. And so I said this earlier, you can expect from start, it's about as much work or effort as you would spend to try to learn how to drive a car. And if you're willing to invest that much time and effort, you'll be very successful with an AFM. So this is an image here of graphene. These are single flakes of graphene. They're 800 picometers high. And this is deposited on mica. You can see right here, this is an atomic step on mica right here across on this corner of this image. And this was a sample that was prepared by UC Berkeley and sent to us. And you can very nicely resolve and see the graphene layers. I just want to point out something on this image. With an AFM, it's you're using what's called false color. So I made this a blue background with nice gold layer. We could make it a white background with black to make it represent more what people think graphene looks like. But the color scale is it's like an artificial rendering, which is available to atomic force microscopes. Okay, so this image was done in a glove box. It's an air-sensitive material by a group at MIT that has one of our microscopes. This is nickel diiodide. And this is an example right here of a single 800 picometer step on that material. Now, the noise floor comes in when you look down here in this region right here. The noise floor on this instrument was around 25 picometers. So they were able to very nicely resolve and measure these step heights on this sample. This is an example right here of a material done at Auburn University, and this is tungsten diselenide. And in this case right here, they had a triangle and without any material deposit on it. And with the organic material deposit on it, they could see a change in the height. And it went from 0.7 nanometers to 2.7 nanometers. Now, one of the things I want to point out in this image, and I'm going to talk about quite a bit here in a little bit, is getting substrates which are very smooth for these kinds of measurements is very important. And so if you take a look at this, this seemingly noise here is not noise, but it has to do with the fact of the surface of the substrate is not that smooth. So a lot of times these substrates have a SA value of about 200 picometers. So if you have 200 picometers, sometimes it can hide the height of the features on the surface. I'll talk about that in a little bit. This is titanium diselenide. It's not a great sample, but it's a really pretty image. One of the nice things about these microscopes is that we get these images from customers or potential customers all around the world. When we scan them, we get these beautiful images. Now, in this case, this isn't what the customer wanted to see, but we like it because it looks like sort of like a Hawaiian t-shirt kind of an image. So we always enjoy getting those kinds of samples. This was done for Purdue University in a glove box, and this was ruthenium trichloride. And again, right here, this is an example of, you can see this single step here is about 600 picometers. It's right here on this edge. And this is a line profile across this feature right here. And this is a line profile on the substrate. And you can see the noise on the substrate is about 250 picometers. That's on this side right here, and that's illustrated by this line profile. So basically, all of the features that you would see to measure the step height are clouded a little bit by this roughness of the surface. Of course, the parts of the material that are 2 or 3 layers thick are very easily resolved in these kinds of microscopes. Finally, this is our last image here. This is an image of graphene. This was done by Jack here at our workshop. And you can see here that this is a chunk of graphene or a flake of graphene. The width of this right here is 270 nanometers across. You can see this right here very clearly. And the height here is 1.4 nanometers. So it's about 2 layers thick. And we can resolve this very, very nicely with the microscope. The scan range here is 2 microns by 2 microns. So, this flake right here is maybe a 1/4 of a micron across. So this kind of shows the capabilities of atomic force microscopes. We're looking at graphene, and you can see that it has very high resolution and very, very good capabilities. Now, one of the things that we mentioned earlier was that you had to be careful about sample preparation, and you had to learn how to do sample preparation. There's a few things you need to look at. Number one is the substrate. Then you have to disperse the material, the graphene somehow, and then you have to get it on the surface, and then you have to dry it and desiccate it. I'd like to point out that there's a very a good technical specification. It's this ISO 21356-1, and this is available publicly, I believe. If you can't find it, you can contact us. We have a copy of it. I think we're allowed to give it out. Terrence, I'll have to talk to you about that later. But anyway, this shows it gives some good insight in how to prepare samples of graphene for scanning with an atomic force microscope. So the substrate is something that's very important. I showed you an image earlier of graphene on mica. That's a very good substrate. It has to be very smooth. It's helpful to have good optical contrast. So silicon oxide, a very thin layer of silicon oxide, can be good because it appears purple, and then you can see the 2D materials of graphene on the surface. Now, this is an example right here of 2 pieces of silicon that we measured here in our applications laboratory. In this one right here, the surface roughness was 104 picometers, but you could actually see the polish marks on the surface of the silicon. And this one right here, is a silicon oxide that we purchased, and it was has a surface roughness SA value of 260 picometers or 0.26 nanometers. So anyway, finding some silicon that's extremely smooth and imaging it before you put the graphene down can be very important. So again, the two materials I think that are most commonly used are mica and silicon for substrates for 2D materials and graphene. Okay, so you have to disperse it. So if you put it in a liquid, you can sonicate it, and that'll break up the chunks, separate them. Depending on your graphene and the size of the graphene and how it's prepared, you might have to optimize the concentration. So, I don't think there's any single number that people can rely on. It depends on the source of the graphene and, of course, how large the material is, those kind of things. So the other thing is you want to minimize contaminants. In the image that I showed you earlier of graphene that Jack measured here in an application lab, you can see there was quite a bit of contaminants in the material. So using ultra pure water can be very important, and anything you can do to minimize contaminants. Once you've dispersed the material, you can put it on the substrate either by spin coating or drop casting. In our case, we've been doing drop casting. That is, just put a small drop of material on the substrate, and then you dry it, or you can spin coat it on. So once it's on the surface, you can either dry it in a vacuum oven, or you can let it dry naturally. Again, keep it in a clean environment. We found a very elegant, inexpensive solution, which was a vacuum oven you could buy on Amazon for about $300 and hitch up to a vacuum pump, and it's on a heating plate, and that works quite well if you don't want to invest in a big, huge vacuum oven. So, so that sort of gives you some insight into how to prepare samples for scanning with an AFM. Again, once you start doing it, you'll optimize it for your particular type of sample. Now, the next topic I'm going to talk about here is the calibration of the AFM. So if you want to use the AFM for getting really high accuracy and high precision measurements, you'll need to really understand how the AFM is calibrated. Now, most AFMs use piezoelectric ceramics to scan the sample or the tip in the XYZ axis. There are some other techniques, but the primary technique are piezoelectric ceramics. And piezoceramics are not linear materials. That is, if you put a voltage ramp, a linear voltage ramp on the ceramic, its displacement exhibits hysteresis. That is, when you're going up, it wants to stay smaller. You're going back down, it wants to stay larger. So this hysteresis can affect the calibration of the instrument. So this is an example right here for a calibration reference sample. These are available from different companies. They're usually test patterns that are made from silicon. And you can use external sensors like strain gauges on the piezoelectric ceramics and use a feedback loop, and you can linearize the motion of the XY axis. And you can calibrate the instrument to within 1% quite nicely with these techniques. And this is an image of one of these test patterns measured on one of our microscopes. This is a 50 micron by 50 micron scan range. And so that works quite well. And you can use that same calibration to zoom in to, say, maybe 5 microns or 1 micron by 1 micron. Now, the XY axis is determinate, so you can predict how it's going to behave. So you can use a closed feedback loop for doing the linearization and the calibration. And the z-axis is a little bit different. It's typically, you cannot do it. The noise on these external sensors is maybe a half a nanometer or 500 picometers. So you can't necessarily rely on these things for accurately measuring the z heights at these levels. So you have to rely on the voltage that's used to derive the z ceramic. Now, if you take a look at in the z-axis, if you take a look at the hysteresis curve versus a linear relationship, you can see curvature. Now, one of the things about an AFM is it's very hard to get the tip exactly perpendicular to the sample. So what that means is when this needle scans across the surface, it puts a linear ramp on it, which puts curvature in the image. And so the external image creates bow in the images, which you have to be aware of. And what happens is if you use the calibration value that you use for the larger features. So in other words, if you calibrate it on something that's say 100 nanometers, and then you want to look at the accuracy of a measurement at 1 or 2 nanometers, it can sometimes be off by as much as say 10%, plus or minus 5%. So sometimes if you really want to do very accurate measurements of sample heights in the AFM of 2D materials, you can use a Z calibration technique, which would be something like the silicon carbide steps. Now, these samples are available on the internet, and there's 2 different step heights. These are atomic terraces, and so they're very, very accurate. And there's one that's 0.7 microns, 0.7 nanometers, and one that's 1.5 nanometers. This is an AFM image here of one of those samples, and this is a histogram of that image, and you can see that the steps are 1.53 nanometers. And so you can use this to calibrate down at the atomic scale to get very accurate measurements of Z calibrations. So you can get down to 1% errors with your height measurements using these techniques. Now, the final subject I have today is, before the demo, is image processing. And one of the things about an atomic force microscope is it directly measures surface topography. And a lot of scientists are used to using SEMs in optical microscopes. And SEMs and TEMs and optical microscopes are derivative techniques. So what you're looking at when you look at that image is a change in the refractive index, or the change in the reflectivity, or a change in the reflection of secondary electrons. And so the image appears immediately in a very sharp contrast. With AFM images, you're measuring topography, and it does not have naturally high contrast. So all images require some image processing. And so the first step is always leveling. Now, I want to point out that the type of image processing you do for visualization of a surface versus metrology is different. And the way you would treat the data is very different. So with visualization, you're trying to create a graphic illustration of the surface to show somebody what you think your graphene looks like. Whereas with metrology measurement, you're trying to get a very accurate measurement. And again, the standards for image processing are very different between those 2 things. So I have here a typical session that would be required to make a pretty picture, to visualize things on a surface with an AFM. So this is what the data looks like when it comes into the microscope. And again, all you see is a tilt, where this is the low and this is the high section here. Now that tilt might be 50 nanometers, but if you're looking for something that's 1 nanometer on that tilt, you can't see it. So the first step you would do would be some sort of a linear background subtraction right here. And once you do that, you can sort of see the graphene on the surface. And then the next step might be to do a histogram adjust to get a little more contrast on the sample. And then when you look at this image, you see these lines here, these horizontal lines across the image. Those lines are created by a small atom getting picked up between the tip and the surface as you scan. So it gets picked up by the tip, it's there, and then it might fall off. And so you'll see these lines across the image. And so you can do what's called a line-by-line subtraction, and that removes that artifact associated with those lines. So you get this image. Now you could do a histogram adjust to make it a little more contrast, and then display it as a 3-dimensional image. Okay, so this entire process here takes about 10 seconds, 20 seconds once you learn how to do it. And then you can create this, beautiful image here. It's a rendering of the graphene. These graphene layers graphene samples are about 1.2 nanometers in height. And so you get very nice contrast on the surface. And again, the thing you have to remember about these microscopes is this is 4,000 nanometers across here, 4,000 nanometers. And this height is like 3 nanometers. So you're getting extremely high contrast on this sample. All right, so that's how you might process an image if what you care about is visualization, if you want to show somebody a nice picture of what you have on your surface. Now, for doing step height measurements, you do a different processing. You would only want to do linear processing. You don't want to do any nonlinear processing because you want to preserve the height information of the image. And so in this case right here, we just did a single line by line leveling of the image. We got this image right here. And then we can measure a line profile. We did it across this flake right here. And you can see we can measure the height was 1.5 nanometers of that flake. Or we can do a histogram measurement, which is shown right here. And the histogram measurement takes into account all of the pixels in the image. And when we did this, we got a height. This is you can see this is the background. That's the lower part. That's the black part in the image. This is the graphene right here. And we got a height of 1.53 nanometers. And again, that takes into account the entire image. And the width of these histogram peaks has to do with the variability in the surface roughness of the sample. So again, you could do either one depending on which one you would feel comfortable with for measuring the height of the material. Okay, so this is two models of AFM. This is just a picture of the stage that AFM Workshop offers. And this is the HR2D. This microscope is developed for MIT to use in a glove box, specifically for measuring 2D materials. And this is the HR AFM, and this is a little more feature rich, costs a little bit more than this microscope. And both of these microscopes cost less than $50,000. And I'm not going to go into all the features and benefits. Jack will mention that a little bit in his presentation. But when we sell these microscopes, when we say a price, that includes the Atomic Force Microscope instrument, a vibration solution, and on-site installation and training. And so one of the things is that this last thing right here can be very important, because in some cases you might select a site for the microscope, and it might be that you move it across the room at a better site. So if a qualified AFM Workshop application scientist is there to help you out with that, that can be very important. The other thing that's very important is after sales support. Sometimes you have questions about how to image a particular type of sample or how to make a specific kind of measurement. And we have expertise here that we can help you with that. Okay, so that was 30 minutes. And I now want to turn the presentation over to Jack. He's going to load, it's a canned demo we did. This is about a 5-minute presentation. And after that, I think we're going to have questions and answers.
Hello, my name is Jack, an application scientist here at AFM Workshop, and today we're going to be talking about the HR AFM and its uses in the 2D material space in both research and industry purposes. AFM Workshop is one of the world's leading affordable AFM producers. We have many customers in both research and industry laboratories, and we look forward to growing with all of you as customers. All right, so here are a few images that were recently measured with the HR AFM. Here we have tungsten diselenide, a couple of flakes of graphene oxide, and a titanium diselenide grown on HOPG substrate. As you can see, this shows both the HR's ability to measure in both lateral size and in the vertical height in the span of nanometers, where some of these flakes have nominal heights in the 1.5 to 2 nanometer range. All right, so we feel it's very important that you get a basic overview of the HR AFM. So I will be explaining some of the key points and features. So here we have a research grade optical microscope. We also have an open design industry standard light lever. We have a universal probe holder. Exchange is very easy. It takes less than a minute to do. We also have an X, Y, and Z piezoceramic scanner, and we utilize a kinematic mount for the stage plate. It helps reduce noise, hence the ability to get the beautiful images that you just saw. Here is a brief overview of our AFM control software. Here you can see that we have aligned the laser. We're running a range check, running a frequency tune to find the resonant frequency of the cantilever, selecting our frequency. adjusting our amplitude of vibration, motoring down, and then beginning the tip approach process. Here you can see that we have navigated to the topo scan window of the AFM control software. We've set a rate of 0.5 hertz and a scan line measure of 512 lines, meaning we will take a 512 by 512 image. This image will take a little bit longer than a typical image, so we have sped up the footage just to make things go a little bit more smoothly. The sample in question is a graphene oxide mixture dispersed on a silicon oxide wafer with a measured vertical height ranging from about 1 nanometer to 3 nanometers, so multi-layer structures. So as we have demonstrated today, the HR AFM is a world-class AFM solution for measuring 2D materials. The HR AFM is designed to outclass its competition in both price and performance for the price. The HR AFM comes with several modes included, including non-vibrating or tapping mode, non-vibrating or contact mode, phase, lateral force, and basic force distance measurements. The HR AFM also has optional modular modes such as conductive AFM, MFM, EFM, liquid cell, and more. AFM Workshop also prides itself in offering a world-class vibration solution called the Q-Box. All of us at AFM Workshop are looking forward to working with you and adding you to our ever-growing list of successful customers. Thank you so much.
Okay, so thank you very much for attending, and I would turn it now over to Terrence and let him run the question and answer.
Thank you, Paul. What I really appreciated was the walk through the theory, the application, and how to apply this, and all the different variables that are important to level setting for the substrate, and then what goes into actually testing the materials. I do have a couple of questions for you, and we definitely have questions from the audience as well. You mentioned a couple of different types of substrate, and I think you very eloquently illustrated what some of the issues are with the substrate if the substrate itself is not perfectly flat or smooth, and that sort of thing. Is there a substrate of preference that you've seen? One is better than another. We usually see it on silicon, but what is the best substrate if there is such a thing?
I think silicon is the preferred substrate, and there's some companies which sell silicon with very thin oxide layers, which give great optical contrast. But again, one of the points is to make sure that you know what the surface roughness of that is before you start looking at your graphene.
Okay. Appreciate that. One of the other issues that we've come across, and this is in our discussions with institutes like the National Physical Laboratory in the UK and other experts that use this, is often graphene, it might be dispersed with a surfactant or some other kind of agent, then it's drop cast or spin cast. And then can you talk about some of the issues with residue on it, or even with a solvent, if you dry it, there might be some residue that's left from that, and how that affects. And a broader question for me is what are the most common mistakes that people make when using this instrumentation?
I think in terms of sample preparation, it's taking the time to get the concentration correct before they do the drop cast or spin cast, because you have to be patient with it and come up with the best conditions for your particular sample. And sometimes, people want to have like a recipe like you'd make a cake. And at this point, I don't think that exists 100% for these kinds of samples. So you have to be a little bit patient with that.
Understood. When we're talking about why we're using this microscopy for graphene or for other 2D materials, often it's to characterize it, which may go into a technical data sheet, in which case we want to measure the lateral flake size and the height to infer layer count, that sort of thing, especially with graphene. And so what that means is to have a relevant number of samples, you can take this image and then you have to decide which of the flakes that you measure. Can you talk a little bit about, maybe approaches or techniques to eliminate bias? Because the operator can look at that and say, okay, I'm going to measure this flake, but not that flake. Is that a relevant question?
Well, I think it is. And I think, one of the things about these microscopes is you only ever see the best image everybody ever measured. Right? You never see, there's a lot of times you'll find, especially with the research publications, you'll see that, somebody measured 200 images and they published one image and they published just a section of that image. And so, that gives a false impression. So I would say that if you wanted to do that, you would set up a protocol and say, look, I'm going to do a 50 micron scan on 7 points on this sample, and I'm going to rigorously analyze those images, right? And stick to some framework or some rigorous framework. And I don't know if anybody has developed that protocol, publicly, but if I was doing this inside a company or a laboratory, that's what I would do.
Excellent. So we have a whole bunch of questions. We'll try to get through as many of them as possible. We do have time until the top of the hour, so we do have a bit of time with that. One of the questions was the limitations that you can measure. I mean, how high of a piece of material becomes too high to measure using this technique?
So that's a good question. In the microscope, you have different types of scanners for different Z ranges. And so, if you have a smaller Z range, you'll get a better resolution, but the largest Z range that we have is 17 microns. So you can easily measure something that's 5-6 microns high with that particular scanner.
Okay. Another one was, I'll interpret it different ways. The question was about, if there are holes or defects in a particular material. So basically the morphology, are there some morphologies of material that are a little trickier? So for example, if you had a single layer of graphene, but you had a defect in the middle of the flake that was maybe, a couple of atoms across, is that something that would be picked up? How sensitive can this get?
We can see down to, pretty much atomic scale defects with the technique. We have something on our website, which is a write-up about what is the resolution of an atomic force microscope. And most people are used to a SEM or optical microscope or TEM. The resolution is very clearly defined as the ability to differentiate between two materials on a surface, 2 points on a surface. In an atomic force microscope, it's measuring 3 dimensions. So you have resolution in X and Y, and you have resolution in Z and combinations thereof. So a lot of times with an AFM, you might see some disruption in the surface and be able to attribute that to a defect on the surface, although you wouldn't actually see all the atoms in that defect.
Got it. You mentioned quite often about correcting for some of the biases, either for, to make sure that it's perfectly level, the fact that you might pick up a single atom on the tip and then it gets dragged across and then it gives you a misreading and that needs to be corrected. All of these corrections, are these automated in the software that you have, or how is that applied?
Yeah, no, we for our image processing, we use it's available. It's, I think, paid for by the European Union. It's called Gwydion software. You can download it from the internet, and we use that. There are software packages out there that will automate the entire process. There's one called SPIP software. It's I think comes out of Europe, out of France maybe. It's a company called Digital Surf, I think. But with those things, you can automate, and do large selections of data by a protocol. For us personally, we just use the Gwydion software, which is again, it's available. It's a open source software.
Excellent. And there's some technical questions. I don't know if you can see any of these, but there will be, if you see something that you want to address, feel free. But I'm going to ask one here. It's about when tuning the cantilever's resonance frequency in tapping mode, why is the lower frequency and amplitude corresponding to higher tapping force, if that makes sense?
Well, sometimes people wonder why, when you measure an AFM image, you use a frequency that's just to the left of the resonance peak.
Okay.
The reason for that is because when the tip starts to interact with the surface, the effective mass of the tip goes up, which causes the resonance peak to shift down. So, something with a higher mass has a lower resonance frequency. So that way, that is actually what gives the sensitivity to the vibrating mode. So that's maybe the answer to that question. In terms of and so that would correspond to putting a slightly larger amount of floating force on between the tip and the surface when you're scanning. So that's correct.
Okay, thank you. There's a question here, and again, for those who know me, I am not a physicist, chemist, PhD, right? So please excuse me if I display my ignorance here. But one of the questions is from a participant who says, we've performed AFM image of graphene oxide films on thin polymeric film or PVDF, whereas the results show a moire effect in the results, similar to 2D materials, layered over each other that give that moire effect. And they were asking how they can differentiate from moire patterns. Is that applicable with the AFM?
Yeah. So one of the things you have to worry about. So most AFMs, as they were originally used, have a laser in them, and a laser is a coherent light source. And sometimes what happens is if you have thin films of materials with certain refractive indexes, different things like that, you can get these moire patterns in the image. Now, we've started using photoluminescent diodes, and they don't have any coherence, and so you don't see those in our images. So you have to differentiate between, what the source of the pattern is. But if you use a photoluminescent diode, it'll eliminate the light source as the source of that pattern.
Excellent, thank you. There's a question that occurred to me, and I see it. One of our delegates has asked that as well. So when we were talking about organic compounds such as polymers, and I would add to that, there are other compounds that oxidize, for example, or might be reactive. Does it matter what solvent is used for the dispersant? And the other related question that I would say, they're talking about THF or chloroform or hexane. From my side would also be, have you seen materials that might undergo some chemical changes while they're being imaged?
Yeah. So that does happen, and that's that's kind of in the category of the mysteries of the universe. One of the things is that you're looking at things at the nanometer scale, and you can't really see it with your eyes. And then sometimes you'd be scanning something and it doesn't work. And then you'd have to theorize, well, what's going on here? Sometimes it's because the material's not adhered to the substrate. Sometimes there's large particles on the surface and you're pushing them around. It could be that the material's degrading. And if you scan, for a couple hours, and you might see it degrading. Could be a chemical decomposition, but you'd have to apply the scientific method to figuring out what the source of that problem is. Now, as you move this technology more towards a production environment or more towards a quality control environment, and you've limited the parameters down, you won't see these kinds of things. And so, if you're in a research laboratory, and we see this all the time, people come in with samples and they have in their mind, they visualize something the way it should be,
Right.
We put it in the microscope and we start to scan it, and they're like, well, that's not what it should look like. And then it's kind of like, well, this is like a camera. We're taking a picture of what it is. This is what it is. I mean, now let's try to understand, modify the model of your visualization or your idea of what's on the surface.
Right.
And so it's almost the immediate reaction of everybody, if they don't see what they want, to blame the instrument. And that's always a tricky conversation.
I hear you. That makes perfect sense. AFM has often been viewed as an excellent technique, but it's also viewed, I have to say, at least this is what I hear, is relatively slow and relatively expensive as a technique. And for many of the graphene companies, concerns about quality control, I don't know of any that are using AFM because of those reasons. But you mentioned, this equipment is under $50,000 for a unit. And can you talk a little bit about, from sample prep to imaging to processing, what kind of time frame are we typically talking about? And I really want to think about this context of, in a production setting, is this a viable tool that maybe companies can start to use for sampling out of production lots?
Right. So I give a talk on AFM for industrial applications. And, I start out by saying, what do you use an AFM? And the answer is use an AFM when nothing else works. Okay.
Okay.
So just start with that. And so the question is, if it's the only thing out there that's going to actually make this measurement, then figuring out how to make it work in your environment and get the right number of samples. But you can prepare a sample and get a scan in 10 minutes.
Okay.
Right.
Well, that's pretty quick.
But that is once you've worked out your protocols and everything. In other words, when you first start, it might take 3 days because you're going to get your concentrations correct. You have to get all these things done. But once you get it limited down, you're using the same kind of samples, the same kinds of substrates, then yeah. So we have customers that are doing diffraction gratings. They do different kinds of polymer imprint things, different things, and yeah, they put them in there and they get images within 5-10 minutes. And
okay. Well, that's pretty quick, and that's quick also compared to alternative techniques.
Right. The thing is to get the focus of the measurement down to something that's relatively well understood. With atomic force microscopes, people come in with different things like, elephant tusks and art from the Louvre, and what does this look like? What does that look like? And of course, if they start doing that with the microscope and they get the thing all out of alignment for the production application, yeah, then it could take some time. But if you use that microscope for production, you do the same thing every time. It's all programmatized. You're just trying to verify something. Yeah, it can go pretty quickly.
That's interesting. There's a question here that says, from TEM images, we know that graphene flakes can be wrinkled. We also, just from what the Graphene Council has done, and we do a lot of material testing, by the way, not ourselves directly, but we work with labs that do the characterization. There's material, for example, that might be turbostratic, right? And it's got different morphologies, kind of looks like an onion ball or something like that, many dimensional. Do those kind of morphologies of the particles that are being measured pose any unique challenges for AFM?
No, in fact, we see a lot of images where the graphene's folded over, and no, it's not a problem as long as the material is adhered to the surface.
Okay.
If it's just laying on the surface, there's no chemical attraction or electrostatic attraction between the material and the surface, then the needle or the stylus can kind of push it aside.
Right. But the level of force that you mentioned is extremely low, right? So the material would have to be quite, I guess, quite loosely placed on the substrate to be moved.
Right.
We do, you showed in your examples, and I appreciated that you showed in your examples quite a wide range of different materials that you had measured. MXenes are a relatively new class of material, and I didn't see that in there. Do you know if your equipment's been used to measure MXene materials at all?
Don't know.
Okay.
We have 300 or 400 customers around the world.
Yeah.
And we sell these things. We try to understand what they're buying it for to make sure we can they'll be successful with it. But I don't know of anybody particularly. We can do a little bit of research into that.
Well, just out of curiosity.
Yeah.
There's more than enough to do with just graphene alone, let alone all these other materials. That's for sure.
Right.
What is the maximum XY scanner range? How big of a sample can you go with this machine?
Yeah, so 100 microns by 100 microns.
Okay.
Yeah,
that's quite good. Excellent. I think that's kind of exhausted most of the technical questions. I don't know if there was anything else in particular you wanted to add, Paul, before we wrap up today.
Nope. If you have any questions about our equipment, feel free to contact us. Our website is afmworkshop.com, and we like to talk to people and find out what their issues and how we can help them solve their problems.
Excellent. Well, on behalf of the Graphene Council, we're really happy to have you as one of our member companies. And for everybody who's listened today and participated, we hope you got something out of today's session. It's our mission to help educate people. And one of the things we do is talk about measurement techniques and characterization, which is so important for graphene and other 2D advanced materials. On behalf of the Graphene Council, thank you, Paul. Thank you and your team for sharing your time and your expertise with us. And for everyone else, thank you for joining. Be safe, and catch us on the next webinar.
Thank you. Bye.
Bye.